Second part of the lecture is on equilibrium equations and conservation of energy. Local equilibrium equation. Equilibrium equations describe how a stress varies within a body. They state sum of all forces acting on a body is zero. In the equilibrium state, everything is balanced. For example, Mr. Potato in the equilibrium state remains as it is. It doesn't explode or it doesn't shrink or expands or whatever. It stays as it is. The force balance equation is written as surface forces plus body forces becomes zero. For surface forces, we have the traction multiplied by ds integrated over s. For body forces, we have density, body forces multiplied by the volume integrated over the entire volume. For the surface forces, we can use Cauchy's stress formula and divergence theorem to get integral of Ti ds equal to sigma ji nj ds integrated over s. That's Cauchy's stress formula. Basically, the stress tensor multiplied by the normal to a surface, and then divergence theorem that maps this field over surface to a field over an entire volume gives us integral of sigma ji comma j dv over v. Basically, divergence of a stress tensor. For example, if I expand this divergence, I get sigma ji comma j is equal to partial sigma 1i partial x1 plus partial sigma 2i partial x2 plus partial sigma 3i partial x3, which is basically the Nobel operator internal product with one column of the stress tensor. Partial x, partial x2, partial x3 dot sigma 1i, sigma 2i, sigma 3i. Substituting in the force balance equation, we get divergence of a stress tensor plus density multiplied by the body forces. dv integrated over v becomes 0, which gives us the local equilibrium equations. Divergence of a stress plus density multiplied by body forces is 0, or in the vector form, divergence of a stress plus rho b is 0. It is called local equilibrium equations. Let's have an example. For a body, the stress state sigma with respect to the reference frame is given by sigma x1 x2 x2 square 0 x2 square x2 x3 x3 square 0 x3 square x3 x1. You see that the stress tensor is symmetric. Find the followings. First, the body force components bi as functions of the coordinates x if the equilibrium equations are to be satisfied everywhere. So the equilibrium equation is divergence of sigma plus rho b becomes 0. For I equal to 1, as a result we get b1 is equal to minus 1 over rho multiplied by partial sigma 1 partial x1 plus partial sigma 2 1 partial x2 plus partial sigma 3 1 partial x3, which gives us basically partial sigma 1 partial x2 is x2. You see here, partial sigma 2 1 partial x2 is 2x2, you have it from here, and partial sigma 3 1 partial x3 is 0 basically. So B1 becomes minus 3x2 divided by rho. The same for B2 gives us minus 3x3 divided by rho, and the same for B3 gives us minus x1 divided by rho. Make sure that you form the divergence of the stress tensor correctly. That's the answer to the first part of this question. Part 2, the stress vector T at point P equal to 1, 2, 3 on the plane was outward uninormal and makes equal angles with the positive coordinate axis. We use the Cauchy stress formula. We can see that the normal making equal angle with all of the positive directions is 1, 1, 1 divided by square root of 3 to normalize it. T from Cauchy stress formula is n dot sigma normal dot the stress tensor. Calculating the stress tensor for point P with coordinates 1, 2, 3 gives us 240, 46, 9093. And doing the multiplication gives us the traction vector to be 6, 19, 12 divided by square root of 3 Pascal. That's the answer to the second part of the question. Linear momentum equilibrium. The principle of linear momentum equilibrium is basically Newton's second law. For a body B with volume V and surface S and velocity V, we can write linear momentum equilibrium as surface forces plus body forces becomes equal to rate of change of linear momentum. Surface forces, as we've seen, is traction multiplied by the differential area. Body forces is rho b differential volume, and then time derivative of density multiplied by velocity integrated over volume. Here T is the traction or stress vector on the surface, and rho is the material density. If the body is cut, like here, once the potato is cut in half, the principle of linear momentum holds for each of the portions. We can integrate over the surface area of portion 1 and volume of portion 1, the same on the surface area of portion 2, volume of portion 2. So basically, we can divide the whole body into sub volumes, sub portions, and still the linear momentum equilibrium is locally valid format. Local equation of motion. We start with linear momentum equilibrium. The surface forces, body forces equal to the time derivative of momentum. And we substitute from continuity equation for d over dt of integral of rho v dv over v with integral of rho v dot dv. So it's like that. It's like rho dot doesn't appear here. We're going to see why later. From Cauchy stress formula for integral of T ds over S, we get sigma ij and I ds integrated over S. And from divergence theorem for sigma ji j nj ds over S, we get the volume integral of divergence of sigma. Know that here we change the notation for simplicity. Finally, by substituting, we get volume integral of rho v dot I minus sigma ji comma j minus rho bi dv equal to 0, which gives us the local equation of motion. Basically, the momentum term or the acceleration term, the momentum derivative terms or the acceleration term, minus the internal, surface forces minus the body forces effect becomes 0. And you remember that sigma ji comma j is divergence of sigma. Here is another example. It says a continuous medium moves with a velocity field of v equal to x1, x2, x3. Note that v is defined in the current frame. The Cauchy stress tensor is a sigma ij equal to x2, c 0, c x3 multiplied by 1 plus t 0, 0, 0, 0, where c is a constant. Find the body force Bi that generates this motion. We start with the local equation of motion, which is rho v dot I minus divergence of sigma minus rho bi is equal to 0. Let's start with calculating v dot. You notice that v is a function of current states, so we need to use the material derivative for the current frame to calculate the time derivative here. dv dt becomes partial v partial t plus v dot gradient of v. That's the material derivative relation. For v dot 1, we get 0 plus v1 partial v1 partial x1 plus v2 partial v1 partial x2 plus v3 partial v1 partial x3. You notice that v1 it's not a function of time, so it's 0, and it's not a function of x2 and x3, so these two terms become 0, and the derivative with respect to x1 is 1, so and v1 is x1 itself, so v1 partial v1 partial x1 becomes x1. The same basically for v2 dot, which becomes x2, and also the same for v3 dot, which becomes x3. Now let's calculate the divergence. For I equal to 1, sigma j1 comma j becomes partial sigma 1 1 partial x1 plus sigma partial partial sigma 2 1 partial x2 plus partial sigma 3 1 partial x3. And you see that sigma 1 1 is not a function of x1, sigma 2 1 is not a function of x2, and sigma 3 1 is not a function of x3, so that becomes 0. The same for I equal to 2, it becomes 0, and also for I equal to 3, all of the elements are 0, so the divergence is 0 as well. Now we can substitute in the equation of motion, noting that the divergence is 0. The equation of motion is simplified to rho v dot is equal to rho b. So basically v is equal to b. So b is x1, x2, x3. And that's the answer to this question. Conservation of energy. So far, you know about local equilibrium, you know about linear momentum equilibrium, and local equation of motion. Conservation of energy deals with kinetic energy and potential energy. For the kinetic energy, K, we can have volume integral of rho v dot v dv, where you already know that rho is density, v is velocity. Or in the notation format, integral volume integral of rho vi dv. On the other hand, we have power, which is rate, time derivative of work. Or in other terms, power is integrand of work. Calculated as P is equal to the external forces, the work of external forces plus the work of body forces. We already know that the external forces are traction multiplied by the differential area, and to get the power we multiply it by the velocity vi, so it's surface integral of ti vi ds over s. And for body forces, the forces are rho bi dv multiplied by the velocity. The local velocity gives us the power associated with those body forces. So it is volume integral of rho bi vi dv over v. We can show that k dot plus s becomes p. So the power basically the work, the power of the work done by the external and body forces plus the kinetic energy of the whole body are in balance by introducing a term S. And S is a stress work, and its integrand is the stress power, which is basically the power of work done inside the body by the stress. In special cases, we can define S equal to U dot. And not always, but in special cases, we can find U that basically differentiating U gives us the stress work. So basically S is equal to U dot, or time derivative of integral of rho epsilon dv over v. And basically epsilon is a specific internal energy or energy density per unit mass. Note that we use continuity equation to simplify this time derivative to rho epsilon dot dv. So basically in special cases, the stress work is equal to the volume integral of a specific internal energy that we show by epsilon. As a result, we get k dot plus u dot is equal to p. The kinetic energy, the derivative of kinetic energy plus the time derivative of internal energy is equal to the power resulted from external forces and body forces. This is the conservation of energy equation. Finally, here is an example for you to work out during the break session before we start the third part of this lecture. it says show that for any property b, I, j, etc., which is a tensor of arbitrary order, that b dot is equal to time derivative of integral of aij, etc., rho dv over v. So basically, b dot is time derivative of another property a multiplied by rho multiplied by dv. We can have b dot is equal to integral of a dot rho dv. So basically, the time derivative is simplified by just time derivative of the property a, and rho dot doesn't contribute. And similarly, the time derivative of integral of rho v dv becomes integral of rho v dot dv. Good luck.